Step back from any fire you have ever known, and it lets you go. The campfire, the candle, the open mouth of a furnace. Move away, and the air softens against your skin. This is one of the first rules your body ever learned, and it has never once failed you. But there is a single fire in the solar system where that rule stops. Right beside the star we look at every single day, the air does the opposite of everything you expect. Close to the surface, it stays merely searing. And then, higher up, out where the heat should be thinning into cold, it climbs instead to 1,000,000 degrees and beyond. Hundreds of times hotter than the surface beneath it. We have known about this for almost 100 years. We still cannot fully explain it, and the number itself sounds impossible. Start with the surface, the part of the sun you can actually point to. We call it the photosphere, the glowing skin of our star. And it burns at around 10,000 degrees Fahrenheit. That alone is hotter than anything you will ever stand near. Hot enough to turn any metal we have ever forged into vapor. Hold that number for a moment, because everything strange that follows grows out of it. Now lift your attention just above that surface, into the thin outer atmosphere of the sun. By every instinct your body carries, it should be gentler up there. Further from the furnace has always meant less heat. Instead, the temperature does not ease off at all. It leaps. Past 1,000,000 degrees, in some regions several million, in the layer of our own star that sits furthest from its core. Not slightly hotter. Hundreds of times hotter than the surface it floats above. Somewhere around 300 times, give or take. Picture standing 10 paces back from a campfire and finding the air there not cooler, but hundreds of times more violent than the flames in front of you. That is the corona, the outermost atmosphere of the sun, and somehow the hottest place in the entire body of our star. And you might wonder how anyone could possibly know the temperature of something no instrument has ever reached out and touched. We read it in light. Hidden inside the corona's faint glow is the chemical fingerprint of iron stripped of 13 of its electrons. A state of matter that can only survive between 1 and 5 million degrees. The atoms themselves become the thermometer. They are reporting a number that has no business being there. But what even is this air around the sun? One small thing while that number sinks in. The same corona is hanging over every one of us right now. The same star, the same impossible heat, wherever you happen to be standing. So tell me in the comments, what part of the world are you watching from? The corona is the sun's atmosphere, the outermost layer made of plasma so thin and so faint that it stretches millions of kilometers out into space. It is always there, wrapped around our star like a second, ghostly body. And for almost all of human history, we could not see it at all. The blinding light of the surface drowned it out. There was only one moment it ever revealed itself. During a total solar eclipse, when the moon slides perfectly across the disk of the sun and the glare blinks out, a pearl-white halo flares around the black circle. People have stood in that sudden midday dusk for thousands of years, frightened and astonished, looking straight at the corona for 2 or 3 minutes and never knowing what it was. The hottest, nearest part of the star we live beside. And for most of our history, it was the thing we saw least. It took a clever trick to change that. In the 1930s, the astronomer Bernard Lyot built an instrument that holds a small disk in front of the sun to block its glaring face, a kind of artificial eclipse made on demand. We call it a coronagraph. Decades later, we carried the idea into space. A joint NASA and ESA observatory called SOHO has watched the corona this way since 1995. And another NASA spacecraft, the Solar Dynamics Observatory, has photographed it continuously in ultraviolet light since 2010. For the first time, scientists could look at the corona every single day instead of for a few stolen minutes once in a lifetime. And what it does next breaks one of the simplest rules in all of physics. Before we go further, a quick and honest ask. If a star quietly breaking its own rules is the kind of thing you want more of, there is now a way to help this reach people who would never find it. Tap Hype just below the player. It takes a second, it costs nothing, and it gives a small channel a real push toward the next curious mind. Here is the rule, the one your whole life confirms. Heat flows from hot things to cold things, never the other way. Pour boiling water into a cold cup, and the cup warms while the water cools until they meet in the middle. So as you move outward from the blazing surface of the sun, away from its source of heat, the temperature should fall. For a thin layer, it does. And then it does the unthinkable. It rockets upward into the millions, as if the cold reaches of the atmosphere were somehow the hearth. We did not stumble onto this gently. Back in 1869, during an eclipse, 2 astronomers named Young and Harkness caught a strange green line in the light of the corona, a color that matched no element anyone had ever catalogued. For decades, people assumed it must be something new, a substance found only up there, and they gave it a name, coronium, a ghost element. It was not until 1939 that 2 physicists, Walther Grotrian and Bengt Edlund, finally cracked it. There was no new element. That green line was iron, stripped of 13 of its electrons, and iron only loses that many electrons at temperatures of 1 to 5 million degrees. The instant they understood the line, they understood the horror inside it. The thin air around the sun was millions of degrees hot, and nothing in our physics said it should be. To be careful with the words, the corona is not actually breaking the laws of thermodynamics. The energy is not flowing backward from cold to hot on its own. Something is actively pumping it up there, something hidden. And for nearly a century, we have not been certain what. Scientists call it the coronal heating problem. One of the oldest unsolved puzzles in the study of our own star, sitting in plain sight above a surface we thought we understood. 1,000,000 degrees right there above us. So why wouldn't it instantly vaporize you? Because a number that large is hiding a second secret, and it is the most useful idea in this whole story. Temperature and heat are not the same thing. Temperature only measures how fast individual particles are moving. Heat is the total amount of energy they can actually hand over to you. A few particles moving insanely fast can carry a staggering temperature and almost no heat at all, because there are so few of them to do the burning. And the corona is almost nothing. Count the particles and you find something close to 1 billion of them in each cubic centimeter. That sounds like a lot until you learn that the surface below holds around 10,000 trillion in the same space. The corona is roughly 1 billion times thinner than the surface. Millions of degrees, yes, but spread across so few particles that there is barely any heat to give. You already know this in your body, even if you have never named it. Hold your hand inside a hot oven, and you can bear it for a while. Plunge it into a pot of boiling water, far cooler by the thermometer, and you are scalded in an instant. The water is denser, packed with particles, so it dumps its heat into you all at once. Or think of a sparkler at a celebration. Its sparks burn at thousands of degrees, and they land on the back of your hand and do nothing, because each one is impossibly tiny. The corona is the sparkler, scaled up to wrap a star, so the temperature is real and the danger is real, but not in the way the number first whispers. Which raises the question the whole field has been chasing. If something is heating this thin air to millions of degrees, what is it? Two suspects have been fighting over the answer for decades. To meet them, you have to meet the real lead actor of the sun, the one quietly running everything. Not fire, magnetism. The sun is a churning ball of plasma, and moving plasma generates ferocious magnetic fields. Fields that twist, knot, snap, and store enormous energy. They are what darkens a sunspot, what hurls a solar flare, what shapes the corona into great glowing arches called coronal loops. Whatever is heating this atmosphere, the magnetic field is almost certainly holding the match. The first suspect is an idea from the physicist Eugene Parker, proposed in 1988. He imagined the corona heated by nanoflares, countless tiny explosions far too small to see one by one. The churning surface tangles the magnetic field lines, braids them tighter and tighter until they snap and reconnect in miniature bursts. No single one matters, but trillions of them together could glow like a furnace that never goes out. The second suspect is older and stranger. Back in the 1940s, Hannes Alfven predicted waves that travel along magnetic field lines like a plucked guitar string carrying a note. These Alfven waves could ferry energy up from the surface and then dissolve into heat high in the corona. For 80 years, it was mostly mathematics. Then, in October 2025, using the Daniel K. Inouye Solar Telescope, scientists watched twisting Alfven waves corkscrewing through the corona for the very first time, the prediction caught in the act. So which is it? The countless tiny explosions or the waves. If you had to place a bet on what is heating the corona, leave it below. Because to settle it, we did something that should not have been possible. We flew a spacecraft straight into the fire. In 2018, NASA launched the Parker Solar Probe, and it has done something no machine had ever done before. It has flown through the corona, through the atmosphere of the sun, and come back without melting. We say casually that it touched the sun. It is worth being honest about what that means, because it is easy to picture the probe skimming the glowing surface, and it never does. The corona reaches millions of kilometers out into space. The probe flies through that outer air, still millions of kilometers above the surface itself. It touched the sun the way you touch the edge of someone's breath. And that turns out to be miracle enough. How does anything survive there? Two reasons, and the first you already know. The corona is so thin that millions of degrees deliver very little actual heat. The second is a shield. On the side facing the sun rides a disk about 2.4 meters across. A core of carbon foam roughly 11 centimeters thick, sandwiched between two carbon plates, painted brilliant white to throw the sunlight back. The face of that shield glows at around 2,500 Fahrenheit. That is hotter than flowing lava from a volcano, and 11 centimeters behind it in the shadow it casts. The body of the spacecraft sits at around 30 degrees Celsius, roughly the warmth of a quiet room. A surface fierce enough to melt rock, and just behind it, an interior cool enough to sit in, and it keeps going closer. On the 24th of December, 2024, Parker made its closest approach yet, passing about 6.1 million kilometers from the surface at around 692,000 kilometers per hour, more than 430,000 miles per hour. The fastest object human beings have ever built, fast enough to cross from New York to Tokyo in under a minute, threading the hottest place near our star. It has held that record again through 2025. We built a thing that flies into a 1,000,000-degree atmosphere and comes home to tell us what it felt. And in 2024, what it told us quietly killed one of the leading theories. For years, there had been a third idea drifting around the edges of the debate. That strange S-shaped kinks in the sun's magnetic field, called switchbacks, might be doing the heating. Parker flew straight through them and measured them up close. And in July of 2024, an analysis of that data ruled them out as the cause of coronal heating. They are real and they are fascinating, but they are not the furnace. One suspect quietly eliminated. The circle of possibilities pulled tighter. Then came something the older explainer videos never had. In August of 2025, a team at Queen Mary University published the first direct evidence of a helicity barrier in the solar wind in the journal Physical Review X. It is a mechanism that changes how the turbulent energy streaming off the sun finally turns into heat. It begins to explain two things at once: why the corona runs so impossibly hot, and why the solar wind picks up the speed it does on its way out. And we could only measure it because Parker was flying inside that environment, sampling the very stuff the theories were arguing about. For decades, this was a question we could only watch from a distance. Now we are taking samples from inside the fire. None of this means the case is closed. The full mechanism, exactly how this thin air climbs to 1,000,000 degrees while the surface below it stays so much cooler, is still open, still argued over by people who have given their careers to it. But for the first time in a long time, the suspects are fewer and the evidence is real, gathered by a spacecraft that completed its 26th close pass in December of 2025 and is still flying as the question waits. And there is a reason we chase it so hard. This thin, impossible layer decides our technological fate. Everything the sun throws at us is born up here, in the corona. This is where the solar wind is launched, a constant stream of charged particles flowing out across the entire solar system, past every planet, past us. And when the magnetic field in the corona snaps the wrong way, it does more than blow. It fires solar flares, bursts of radiation that arrive at the speed of light, and coronal mass ejections, clouds of billions of tons of plasma flung toward the planets. Understanding the corona is not a curiosity. It is how we learn to see those blows coming. We know what they can do because they have done it. In 1859, a storm we now call the Carrington event struck a world that had only just strung up the telegraph, and the wires sparked and caught fire across continents. In 1989, a lesser storm collapsed the power grid across Quebec and left millions in the dark for about 9 hours. In July of 2012, a storm strong enough to rival Carrington tore through Earth's orbit and missed us by roughly 9 days.
Without the electric grid, well, of course, there's no power. There's also no water. There's also no communications, no transportation, no medical care. The financial system would be down.
One estimate put the cost of a direct Carrington scale hit on our modern grid at around $2.6 trillion. But this is not a story about being helpless beneath the sky. It is the opposite. The very fact that we watch the corona is what gives us warning. When a storm is rising, satellites see it leave the sun, and grid operators can shed load and brace the network before it arrives, the way a city boards its windows ahead of a coming wind. The more honestly we understand this layer, the less it is a thing that happens to us, and the more it is a thing we can stand ready for. Which brings us back to where we started, to the strange, faint air around our star. So here is what we are left holding. The hottest place in the solar system is not in some distant, hostile corner of space. It is wrapped around the one star we have looked at every day of our lives, the one our ancestors named and worshipped and told time by. It hangs above a surface we thought we knew, breaking the gentlest rule we have, that moving away from a fire should let you cool, and it has kept its secret for nearly 100 years. We have flown a machine into it. We have narrowed the suspects. We still cannot say with certainty what lights it. Think of how strange that is. For thousands of years, the only glimpse anyone got of this place was a halo flaring around a darkened sun for 2 or 3 minutes once in a lifetime, if you were standing in exactly the right shadow on Earth. The hottest thing near us was also the thing we almost never saw. And now, after all of that, we can watch it every day, fly through it, weigh its particles, read its temperature in the color of stripped iron. And the oldest question is still the one we cannot answer. Not because we are careless, because the sun is harder than it looks. And the answer may already be on its way. Right now, somewhere out past the orbit of Venus, a small craft is falling sunward again. And the data that finally closes this case may be traveling toward Earth at this very moment, a faint signal crossing the dark. The same fire our species has warmed itself beside since before we had words for it still holds something back. We happen to arrive late in a very old universe, awake just long enough and curious just enough to look up at the flame we have always known and finally notice that we never understood it at all. That is not a smallness. That is the privilege to be the brief, waking things that get to ask,